In this elephant bite of this great big chapter 2, we're going to talk about the chemistry of water and the chemistry of carbon. So first, let's talk about water. And here are your learning objectives. And I'll talk about water first, and then we'll talk about carbon chemistry after that. So one thing I want to impress upon you is that water is weird. It is a strange chemical compound relative to other chemical compounds, and that probably sounds very odd to you to hear because water is so mundane. It's all around us. It's makes up a vast majority of your body weight is water weight. So hopefully I'll be able to qualify this statement for you. So it's weird compared to other compounds, and this is chapter 2, part 2. Water everywhere comes in so many different forms. The oceans are full of water, freshwater lakes, tornadoes, clouds are just made up of water and dust floating up in the sky. Um, and living organisms depend upon water. This is one of the qualities that we don't really talk about as a quality, but it's a physical property of life as we know it, is that it requires water. So let's jump ahead to learning objective 9 before we hit on learning objective 8 and describe the properties of water. Okay, well, the properties of water can be traced back to this diagram, which maybe you remember from the previous lecture. This is a water molecule, H2O. There's an oxygen atom with 2 hydrogen atoms, and they are covalently bonded to each other. But oxygen and hydrogen don't have the same affinity, they don't have the same pull on electrons. So oxygen is going to pull electron density, or the amount of time the electrons spend around the oxygen atom is going to be more than the amount of time the electrons spend around the hydrogens. And what this means is because of this polar covalent bonding, you end up with partial positive charges by this lowercase delta plus, and a partial negative charge indicated by this lowercase delta minus, that they're not full formal charges, but there is enough of a disparity at either ends of the water molecule that it affects the chemistry of it. It makes them kind of stick together. So 4 main properties of water that are conducive for life are enumerated here. So water molecules cohere to each other. They stick together. And that means that water is good at moderating temperature, so you don't have dramatic temperature swings in living organisms. Ice floats, and what does that have to do with living organisms? I will explain that to you. And then the fact that water is polar, has this polar covalent bond and hydrogen bonding, makes it a very, very good solvent. And we'll talk about that. That's part of learning objective 8. And all of that can be traced to hydrogen bonding, that intermolecular bonding between water molecules and other molecules, including other water molecules. And it looks kind of like this, just if you had pure water and you were able to zoom in and look at the molecules whizzing around, this is what you would see, is that those partial positive charges would be attracted to partial negative charges, and vice versa. So the shape of a water molecule, you notice that the hydrogens are not on either side exactly. It's not like a straight line from an H to the O to the H. It's kind of got a little bend to it, a little angle to it. And that's really what happens because of the way that the electrons are shared. Now, that stickiness of water molecules to each other has a number of effects that we can see with our naked eye. So this is an insect called a water strider, which maybe you've seen around. And it's on a pond with a bunch of duckweed, which are those little green dots. Those are leaves of duckweed. And both of them are able to stay on top of the water and not sink down into it because of surface tension. Water molecules stick together and they prevent that organism from sinking down into it. So why can't we just sort of walk on water all the time? Or really ever? Because we have a lot more mass. If we were standing on something that was able to displace the water better, like a surfboard, stand-up paddleboard, canoe, kayak, they would float on top of the water. But if we were to stand on a liquid that was in the same stickiness, so to speak, like if you were to walk across a big lake of marshmallow, that's a liquid that's viscous enough that it would support you, just kind of like this water strider is able to be supported by the surface tension on this pond. So in addition to surface tension, water is really good at moderating temperature. So I mentioned energy, and we're going to keep talking about energy. It's going to come up again and again and again as matter doing things. Energy is the capacity for something to do work or affect change. Okay? That's the basic definition of what energy is. It's things doing stuff. So let's talk about heat versus temperature. So the heat of something is the total kinetic energy of all the molecules. What makes something warmer versus colder if it's the same thing? So if you had a balloon full of gas, like helium gas, the molecules are going to be moving around in there. But if you heat it up, then the molecules are going to move more quickly. They're going to have more kinetic energy. It's kind of like, a car driving down the interstate has a lot more kinetic energy than a car that is driving in a parade and going very slowly. The potential for that car to do some damage is a lot greater if it impacts something on the highway versus if it impacted something going 5 miles an hour. Whereas temperature is the average kinetic energy of molecules in a particular substance. So specific heat is a way to describe a physical property of materials, and is the amount of heat or the amount of shaking of molecules required to change temperature. So water, because it's so sticky, it changes temperature less rapidly than other substances. So to give you an example, if you put an empty kettle on a stove and turn the heat on because you forgot to add water to it, in a very short amount of time, the metal, just the bare metal, is going to heat up very quickly, and hopefully you don't burn your house down. But this is why, say you want to boil some spaghetti, and if you've done this before, you're probably like, why does it take so long to get that water boiling? And the reason why is because of the hydrogen bonding. So it just takes forever, it seems, to get that water from just room temperature up to the boiling point, which is 100 degrees Celsius or 212 degrees Fahrenheit. And the reason why is because those water molecules are bumping into each other and they're sticking a little bit. So they're resisting moving faster because they bump into each other and they stick a bit. Bump into each other and they stick a bit. So one of the implications for that, besides just having organisms full of water so they don't change temperature very quickly. So imagine if we were made out of metal, we would change temperature in the sun so quickly that our bodies wouldn't be able to acclimate. And water in the atmosphere has a very similar kind of effect on climate. So this is a picture of the coast of California, Southern California. And you can see that this is kind of a weather map showing you the daily temperatures in degrees Fahrenheit um, along the coast, Santa Barbara, Los Angeles, San Diego, into the Central Valley, where the weather it's a lot drier. It's a desert. So you can see like out in San Bernardino, Palm Springs, that's in the desert, and the air is much drier out there. So the coast tends to be much cooler. And why is it? It's because there's a lot more humidity, a lot more moisture in the air. The ocean, as a large body of water, absorbs heat, and it resists changes in heat. So the difference between day and night temperature along the coast is not very much compared to in the desert. So these are daytime temperatures. During the nighttime, the temperatures along the coast aren't going to drop that much, but out in the desert, they're going to drop a lot. And that's because air has a much lower heat capacity. It changes temperature a lot more easily than air that's saturated with moisture, water. Okay, so maybe a long time ago you took a science class and they talked about these three states of matter, and you learned that gases are less dense than liquids, and liquids are less dense than solids. So, why does ice float? So, ice is frozen water, and since ice is the solid form of water, and solids are more dense than liquids, it should sink. It's more dense. If it's more dense than the liquid water, that means it's going to sink. But water floats. Ice floats in liquid water. Why does it float? Again, it all goes back to the activity's hydrogen bonds. When water is in the liquid form, the hydrogen bonds are forming, reforming as the water molecules bump into each other. They stick a little bit, and they move on. But when water starts to form into ice, the hydrogen bonds start to stabilize at a fairly consistent distance from each other. So because those hydrogen bonds stabilize, it makes ice less dense than liquid water. So ice floats. And you can also see it forms this nice kind of hexagonal, six-sided shape, structure. It's three-dimensional, and that's why snowflakes are hexagonal, because this is it's crystallized ice. So you can see that the shape of what's happening at the molecular level occurring in snowflakes. And why is that important for life? Because as you can see with this shrimp here, if water froze and then sank, it means that in the winter, a body of water would freeze from the bottom up. And living things would have a hard time living in that frozen water. Whereas this shrimp, as you can see here, gets to live under the ice. The ice actually serves to insulate water and keep a little bit of liquid water so that those shrimp can still swim around and survive, rather than being frozen solid, because being frozen solid, that's very disruptive to the tissues of the shrimp. So life can survive because this ice forms a sort of an insulating barrier at the top.